All right, so why don't we get started? You'll all notice that Scott is on vacation, so you get me and Alex today, in addition to our usual cast of characters. So, hi everybody. Um, all right, so welcome to today's ACS DOC Virtual Symposium, where we have Professors Tom Rovis and Ohyun Kwon. Before we get started, I'll go through some announcements, just some DOC stuff. It is the time of year where we recognize our a number of members of our division in the form of our divisional awards. So just wanted to congratulate this year's winners. First of all, the Technical Achievement Awards in Organic Chemistry, which for the second year has been split into kind of early and mid-career categories. And this award recognizes chemists with their bachelor's and master's. There were 20 winners representing a large number of companies. So congratulations to everybody. In addition, this year, the Division of Organic Chemistry partnered with the Divisions of Analytical and Medicinal Chemistry for our early career Industrial Chemist Award. We also have, as has been going for a few years now, our mid-career award. So these recognize independent industrial investigators with either up to 10 or 11 to 25 years of experience. And if anybody has any questions, there's the names of the chairs. Myself and Steve Wisniewski are listed, so feel free to contact us. But we've recently announced this year's winners for both categories. The names are on the slide. It'll be on social media soon. So congratulations to everybody. Other upcoming events. The 49th National Organic Chemistry Symposium will be held from June 22nd to 26th at Rensselaer. Really phenomenal lineup of speakers. It's the 100-year anniversary of the National Organic Chemistry Symposium. Registration is open, and we hope you'll be there. And of course, the winner of the 2025 Roger Adams Award is Professor Eric Jacobson. So he will be the keynote speaker at that National Organic Symposium. He is also conveniently the winner of the 2024 Tetrahedron Prize. And so he will be giving his talk at the fall ACS meeting. So join us. So we hope you'll join us for that. One last thing, a little bit, I guess, self-indulgent as I'm working on this one. But if you're in the Mid-Atlantic, Northeast or Northeast region, you're interested in a regional meeting, MARM 2025 is open for registration. It's being held from May 28th to 31st, and we have a phenomenal lineup of speakers: Professor Morton Meldal, Dr. Phaedra St. Hilaire, and Dr. Rebecca Ruck are our keynotes. So there should be a nice meeting. Hope you'll be there. And lastly, our upcoming symposium will have Professor Abby Doyle from UCLA, as well as Nate Kundis from Gilead to talk about lenacapavir. So we look forward to that in 3 months. All right. So I guess with that, we can get started. Tom, if you want to share your screen, I can introduce you. So our first speaker of the session is Professor. Oh, before I do that, if anybody has any questions during this meeting, there is a box to type them into. So please feel free to ask them, and one of us will relay them. All right. So our first speaker of the session is Professor Tom Rovis. Tom earned both his bachelor's and PhD at University of Toronto, pursuing doctoral work with Professor Mark Loudons. After his PhD, he moved to Harvard, where he pursued postdoctoral studies with Professor David Evans, performing some mechanistic work on copper-catalyzed aldol and Michael reactions. In 2000, he began his independent career at Colorado State, and then moved to Columbia in 2016. Tom is known for his fundamental work in both NHC and rhodium catalysis to access complex substrates, both in organic systems as well as the generation of metalloenzymes to do rhodium chemistry in aqueous environments. His lab is very active in photocatalysis. He's published some really novel work in low low energy photoredox catalysis. And for this work, Tom has received, too many awards to name, but a couple of them are the Alexander von Humboldt Foundation Fellowship and a Cope Scholar Award. So today he will talk about redshifting photoredox catalysis.
Thanks, Steve. Thank you and all the organizers for the opportunity to be here. I'll tell you a little story that began in my lab about 8 years ago. And to preface that, I really like showing this slide, which I hope you can all see, which is a picture that was taken in my lab, probably just before the pandemic now, actually, so several years ago. And I'll also say that the only thing we did to stage this picture was that we turned the lab lights off. And of course, as I think many of us that work on photoredox catalysis recognize, usually these lights are shielded by something. We also took those boxes down to get the impact. But what can you see in here? You see on the far right-hand side of the screen here, you can see a blue light Kessel. There's a reaction right in front of it. There's the Kessel that you can see. On the far left, you can see a red light, Kessel, and then intermediate here, you can see an orange light. And maybe the question arises, why do you care about 3 different wavelengths of light? And the answer is because they're not the same. So if you look at the electromagnetic radiation spectrum, we have radio waves on one side, and I think all of us recognize how innocuous radio waves are. We have gamma rays on the other side, and similarly, we all recognize how destructive gamma rays are. Well, the visible is a tiny little sliver buttressed by ultraviolet on one side, again, bad, infrared on the other side. And if you blow up the visible from the purple to the red, 400 nanometers on the purple side, 700 nanometers on the red side, maybe even more instructive is the corresponding kilocalories. 40 kilocalories per mole for red light, 400 nanometer light, on the other hand, 700 kilocalories per mole. So we, as a community, tend to do photoredox here. Blue light, 450 nanometers or so, that's about 63 kilocalories per mole. And the majority of reactions that we run with photoredox are reasonable room temperature transformations. And of course, they tend to have barriers of about 20 odd kilocalories per mole. And yet we have for a reasonable rate. And yet we use 63 kilocalories per mole light to drive those reactions. I would argue that it's overkill. Much more interesting, I would say, is to do chemistry with lower energy light. So central to this talk is photoredox catalysis. And just to give maybe a few people out there that are unfamiliar with the mechanism of this, here's a prototypical mechanism. It's illustrated for ruthenium tris bipyridine, or so-called RuBiPi, which is a very common photoredox catalyst. RuBiPi has a ground state D6 metal-centered HOMO and a ligand-centered LUMO. Irradiation of RuBiPi with blue light, 450 nanometers, raises the electron from the HOMO into the LUMO. That gives you this, drawn here as a singlet, but it becomes a triplet. I'll talk about that in just a second. This ruthenium-2 excited state, which has an extra electron in the ligand sphere, and therefore it's a reductant. It has a hole at the metal, and therefore it's an oxidant. And in fact, it's both. I illustrate here an oxidative quench, so an electron is removed. That generates an even stronger oxidant, this ruthenium-3 intermediate, which can do lots of things, including oxidize tertiary amines to the corresponding radical cations, as I've demonstrated on this slide. That process obviously closes the photoredox catalyst cycle and then initiates some downstream organic transformation, in this case at the amine, presumably. Now, a couple of things about this. One is that the redox potentials of both the front and the back are measurable / estimatable, and I'll talk about how we do that in just a couple of slides. And secondly, of course, as synthetic chemist, that means we can manipulate not just the ligand environment by changing the ligands around the ruthenium, but we can also manipulate the metal, not to mention going into some organic photocatalyst. And we can tune, although not perfectly, and I'll talk about that, these redox potentials to get the desired transformation that we want. Okay, so there's actually 3 different cohorts, 3 different mechanisms of photoredox catalysis. There's the photocatalyst as oxidant, which I demonstrated on the last slide. There's the photocatalyst as reductant, which in essence, the photocatalyst delivers an electron to the acceptor molecule. That obviously becomes reduced. The photocatalyst itself got oxidized. And the third situation is energy transfer, which is in essence both. So the excited state of the photocatalyst drawn here as its triplet. One electron hops over to your molecule of interest. The molecule of interest delivers an electron back at the same time. This is dextran energy transfer. That gives you the ground state of the photocatalyst, and of course now a triplet of your molecule of interest. And then triplet reactivity can be induced from whatever that molecule is. And all 3 of these are, I would say, fairly active areas of research in many labs around the world. All right, so why do we care about low energy light? why do we want to use lower energy light? Well, there's three different sort of umbrella reasons for it. One is that presumably lower energy light can penetrate deeper into, for example, reaction vessels. So because of the Beer-Lambert law, if the extinction coefficient is lower, you can get a deeper penetration. And we've demonstrated that. Actually, I'll show you a picture of that a little bit later. Secondly, infrared light or low energy light can presumably penetrate things like materials, like various materials. And I'll show you a little bit about that so you can imagine doing a polymerization on the outside of a barrier of some kind, like, for example, in a mold. And I'll talk a little bit about this. And the last one, of course, is that the most interesting barrier that red light can penetrate is biological tissue. There's various cartoons that you can find on the internet. Here's one of them. The penetration in the deep red to near infrared is deepest into tissue. And in theory, at some point down the road, we can think about actually doing chemistry inside people. Blue light also, by the way, is somewhat cytotoxic. I think this is a very interesting area that I will not cover in this lecture today. So we got into this area probably about 7 or 8 years ago now. And at the time, the problem in the area was encapsulated by this review by Ian Davies and Dave McMillan, who argued, in essence, that many photoredox reactions are photon limited. What does that mean? How we and everyone else tends to set up these reactions is the light source these days, at least, is the Kessel lamp. We irradiate the reaction vessel. The vessel is almost inevitably a vial. The light, of course, enters the reaction vessel and is absorbed by the species inside that absorb the light, including, of course, predominantly the photoredox catalyst. So that relationship, the penetration of the light as a function of distance inside the flask as a function of extinction coefficient, is known as the Beer-Lambert law. And it's illustrated here graphically. So at 0.5 millimolar Rubippi, the transmittance of the light from 100% inside by a function of distance, you can see here 1 millimeter, 2 millimeters. 2 millimeters inside the flask is about 5% transmittance. 1 millimolar solution, of course, drops off more precipitously. So what does that mean? That means, in essence, in these vials, the chemistry that the activation of the photocatalyst happens entirely on the outskirts of the vial. And of course, as you go larger and larger vessel from a vial into a round bottom and ultimately, of course, into batch scale process chemistry, the chemistry still only happens at the first millimeter or two on the outside of the vial. So what can you do about this? We can clearly use mirrors to focus the beams, but that's still a two-dimensional problem because it still comes from the outside. You can put a light source inside the vial, but if you put one light source inside the vial or the flask or the round bottom, it's still a two-dimensional problem. Really, what you need to do is you need to create 1 million light sources inside the flask. So we wanted to use infrared radiation for several reasons, one of which is infrared radiation is penetrating. This is a picture of a gentleman with a regular camera, a visible light camera. Obviously, you can't see the arm through the black plastic bag, but infrared camera shows you the arm because it penetrates black plastic. There's a so-called optical window in mammals, which is 600 to about 1400, really about 600 to 1000, which is the most interesting area of it, I would argue. And perhaps as a kid, you held up a flashlight to your face when you were camping, and what happens? Your face glows red because, of course, it's the red that penetrates, but not so much the other wavelengths. IR is also ubiquitous. More than half the energy of the sun is infrared. What's the problem? At least as judged 8 years ago, the problem was one of perception. And that is that infrared radiation, that's about 35 to 40 kilocalories per mole, was simply insufficient to drive photoredox reactions, which again were thought, wrongly, as I'll get to require 60 odd kilocalories per mole. So initially, our solution was simple. If one photon of red light gives you 35 kilocalories per mole, simply use 2 photons. And that's a process called upconversion. So this chemistry was done collaboratively with my colleague Luis Campos here at Columbia, as well as Dan Congreve, who was at Harvard, now he's at Stanford. The student in my lab that did this work is Ben Ravitz, who's now at Genentech. So how does upconversion work? So upconversion uses a molecule that I'll call a sensitizer. It's basically a photocatalyst, and I'll show you the structure of these in just a second. The sensitizer absorbs a photon of light. That gives you the excited state singlet. There's an intersystem crossing event that happens from the singlet to the triplet. That sensitizer triplet then encounters a molecule in solution, I will call it an annihilator. As long as the triplet energy of the annihilator is close to the triplet energy of the sensitizer, i.e. these two are reasonably close, triplet sensitization occurs. So from the excited state triplet of the sensitizer, you get excited state triplet of the annihilator, and of course a ground state singlet of the sensitizer, okay? This happens twice in solution, another photon, and it radiates another sensitizer to give you another triplet, which encounters another annihilator. And now you have two triplets of the annihilators next to each other. When they encounter each other in solution, one of these is going to go up to the excited state singlet, and the other one's going to go down to the ground state singlet. As long as that the excited state singlet is less than twice the energy of the triplet, i.e. you cannot create energy. Okay. What happens then? You've taken these two low energy photons, you've created one high energy excited state. The excited state can then do several things, emit a photon of light, and I'll show you that. We can also do chemistry, do photoredox catalysis. So what does that look like? We started with this palladium phthalocyanine as a sensitizer. That's this molecule over here. This absorbs in the green. As you can see in the trace here, we will irradiate on the shoulder about 780. The annihilator that we started with is this furyl dipyrrolopyrroline, which emits in the orange here. The picture of the vial here, this is an infrared beam that comes in, and that's creating orange photons inside the flask, right? So we're creating these light sources, in essence, little light bulbs, all throughout the flask because the upconversion creates a higher energy photon inside the flask from lower energy photons. What can you do with orange light? Well, about 8 years ago, not much, but you can activate ESNY, which reduces these alpha bromoacetylphenols, these phenones, these aryl diazoniums to the aryl radical, which cyclizes. Chemistry that was known with higher energy light, but we're using infrared light to drive these processes. But we really wanted blue, and to access blue, we needed this platinum porphyrin as a synthesizer that, again, absorbs here in the green at 700. We will irradiate on the shoulder about 730. This tetraterpbutylpyrroline is the annihilator, and that emits blue. And now you can see the infrared beam comes in, and it creates this bar of blue photons all through the flask or through cuvette. And blue, of course, activates RBIPI. And RBIPI does several things, including this 2+2 cycloaddition initially reported by Ohyun. The yields, dietary selectivities are in essence exactly the same with infrared light as they are with blue light, but of course, a much lower energy input. In fact, you don't need RBIPI. The pyrroline is a fine photoredox catalyst of its own. It's reductive. These divinyl azids extrude N2 to give you cyclization to the pyrrole. Or this bottom reaction is the initiated reduction of this alpha bromoacetate by the photocatalyst, and that causes a polymerization of methacrylate to give you polymethyl methacrylate. Molecular weights and polydispersase are identical to what Rita Alanis and Hawker reported, except they use blue light, and we're using infrared light to drive this. So this last one gave us an opportunity to assay the penetration of various materials with infrared light. And to do that experiment, we set up the following. We took methacrylate in the presence of this cross-linking additive, which of course, upon polymerization, would give us a heavily cross-linked polymer to the point that it's really just a piece of plastic. Inversion of the vial at the end of the reaction, if it worked, it'll result in this freestanding gel that doesn't flow. If it didn't work, obviously it'll flow down the sides of the flask. I'll show you the setup. This picture here is demonstrated for the green vial at the back is the reaction vessel. The orange vial that's in front of it is a solution of RBIPI in front of the vial, so it's not in the reaction. The diode is the source of the infrared light. Sorry, the spotlight is a little bit slow to respond. There's two lenses to focus the beam, and then again, the barrier's in front. And we invert it at the end, and if it stands up like this, it worked. We did several barriers. The bottom picture here is of another barrier. We wrapped the vial in bacon. Why did we wrap the vial in bacon? Well, it's obviously a very cheap and really available surrogate of flesh, right? And then the outcomes. So near infrared light, air, water pass both blue and near infrared. Big surprise. Amber glass stops blue light. Bacon stops blue light. Bacon burns with blue light. RBIPI, long pass filters, white silicone sheets, 3 sheets of white paper, hemoglobin solution, pigskin, all stop blue light, all of them allow infrared light through. And that was published, as you can see, several years ago now. So I really am very proud of this paper in the direction that it has taken us, but it's a very flawed paper in that we tried a lot of reactions, only about 6 of them worked. But that process told us something fairly fundamental, and that is the directions to go to try to improve this chemistry. The big problem was the sensitizer. These platinum porphyrins or palladium phthalocyanines were flat. That tended to restrict the solvent choice. Of course, you can modify them to make them more soluble, but it also was sensitive to the addition of radicals to the porphyrins. And of course, many photoredox catalyzed reactions these days invoke and generate radicals. And what would happen if the radical actually adds to porphyrin, by the way, that changes the photophysics and the reaction shuts down. So that was a big problem. We wanted to get away from these flat sensitizers. The other problem was more subtle, and that was the one of energy input. So I draw here the sensitizer, which again, irradiation of a ground state sensitizer gives you the singlet excited state, and then an inter-system crossing event gives you the triplet. Okay. What does that look like? So for Rubipi, irradiation happens at 450, that's 63 kilocalories. So the singlet is at 63 kilocalories above, but the triplet is 46 kilocalories, i.e., as soon as you generate the singlet, and you have an inter-system crossing event to the triplet, and you've lost 17 kcals. For Rubipi, this process takes about several picoseconds, i.e., is in essence immediately as you generate the singlet, you've got the triplet, and you've given up 17 kcals. So it's a waste. The case for the palladium phthalocyanine is not quite as bad, but similar, 39 kcals for the singlet, 28 for the triplet. And the platinum porphyrin is the best one, but it's still 41 at the singlet, 35 at the triplet. Every single time you have a loss because of this, you can't go directly from the ground state singlet to the excited state triplet. So Ben found a complex in the literature that's actually been known a long time before, but has also been invoked in upconversion by this paper in 2017. These osmium terpyridyl complexes. These absorb in the blue traces you can see here, and the absorption is actually extremely broad because it's in essence in the entire visible range. The emission is in the red here, but you can see that there's overlap between absorption and the emission, and that allows these things to do something that it's not supposed to do, which is called a spin-forbidden excitation. Because you have this overlap, you can go directly from the ground state singlet to the excited state triplet because osmium is a heavy element and because of what's called spin-orbit coupling. That means you can irradiate with 39 kilocalories of energy, and you can get 39 kilocalories of triplet energy out of it. And with this, you can do upconversion. So we generate these with the parallel annihilator, we generate blue light. The picture on the right here is the most diffuse source of light that we have, of red light that we have, and you can clearly see that we're generating blue photons inside the flask. So with this, we could do reactions that we couldn't do before. Like, for example, the Umamoto reagent, the trifluoromethyl radical is generated, it adds to the styrene. The reaction generates a cation at that benzylic position and chloride traps at the chlorotrifluoromethylation. Whoa. Sorry about that. So of course, we did several experiments, control experiments, and because Ben is a careful experimentalist, a scientist, he left out the annihilator and the chemistry still worked. And this, I would argue, was really transformative for us because what it made us do is it made us start to look at some of the numbers involved here a little bit closer. So I'll go through what these numbers really mean in just a couple of slides, but basically all I need you to look at is the excited state and ground state redox potentials for this osmium catalyst and compare it to the same numbers for Rubipi. 0.71 volts for osmium, 0.77 for Rubipi. Minus 0.6, minus 0.8. They're not exactly the same, but they're similar and they're in range of each other, except osmium irradiates in the near infrared at 39 kcals or 740 nanometers, and Rubipi irradiates in the blue. That means we think we're getting photoredox catalysis with infrared responsive osmium catalysts. Is that really true? So we also ran the reaction with the Tony reagent instead of the Yamamoto reagent. That chemistry also works if you have the annihilator, but it does not work without the annihilator. And the reason makes perfect sense when you consider that the Umamoto reagent is far easier to reduce than the Tony, and the osmium photocatalyst can reach the reduction potentials necessary for the Umamoto, but not for the Tony. So osmium is really its own photocatalyst. We did several other reactions to demonstrate this. One was we generate these photoacids by excitation of diphenyl iodonium, and that polymerizes styrene oxide. We initiated atom transfer radical polymerizations as well as RAF polymerizations, all with near infrared driven near infrared light. We also reduced several metals. We reduced copper 2 to copper 1 to do a click reaction. We reduced cobalt 2 to cobalt 1 to do a 2 plus 2 plus 2 cycle addition. And then we also generated singlet oxygen with a different catalyst now. These oxidized aryl boronic acids to the phenols, or alternately furfural to these butyrolactones. This bottom case, we actually tested to see what the catalyst loading. We went lower and lower and lower in catalyst loading. And the bottom example here is the most excited I've ever gotten, about 7% yield, because we're getting 70,000 turnovers. These are robust catalysts, and I think they'll stand up to a lot. I mentioned scale up earlier. So the osmium catalyst will also absorb in the blue. Of course, the extinction coefficient in the blue is much higher. They absorb better in the blue than they do in the infrared. But what that means is that the beam can penetrate deeper into solution in the infrared at the lower extinction coefficient than it can in the blue, as illustrated here more or less through the entire 2-liter round bottom with red light, but not so much with blue light. And in fact, we can do mole scale photoredox catalysis. We did this with colleagues in Bristol Myers Squibb across the river, where we took a mole of this pyridone and did one of Corey Stevenson's published reaction, trifluoromethylation, 62% yield overnight reaction. And that was published, as you can see, several years ago. I want to dovetail into sort of a different direction that we've taken this chemistry more recently. And to set that up, what I would like to tell you about is how we tend to characterize these photocatalysts. So we usually do, and of course the entire field does this, we take a cyclic voltammogram that gives us the redox potentials, the reduce in both the oxidative and the reductive way, and that's these numbers, minus 1.36 and plus 0.9784 for the various couples. Then we take an absorption emission to show us both the singlet energy and the triplet energy, and then we assign this intersection between the singlet and the triplet where the overlap, where the spin forbidden excitation is, as the triplet energy. It's not perfect, but it's a good estimate of it. And then we take those numbers and we punch them into the Remueller equation, and that's the ground state redox potentials plus and minus the triplet energy to give you the excited state redox potentials. What does that look like if you do this? So you take, for example, for osmium, the 2 excited state to osmium 3, 0.9784 minus 1.91 electron volts equals minus 0.936, or the reverse is plus 0.546. Why am I walking through all of this with you? So if I show several of the common photoredox catalysts, and illustrated here on the far left is one of the workhorses, right? This is the iridium DFCF3. This is broadly used in the community, including by us. It is responsive to purple light, 380 nanometers, with a triplet energy of about 60 kilocalories. Right next to it, I've illustrated Rubipi, blue light, 455 nanometers, 46 kilocalories of triplet energy. And then one of our osmium catalysts is on the far right here. In the deep red, 678 nanometers, 43 kilocalories of triplet energy. We were interested in going after a different reaction, and that is this sp3-sp2 cross-coupling, which has been demonstrated by others, which involves various alkyl functional coupling partners. And I'll talk about some of them a little bit later, to generate an sp3-sp2 bond, usually almost inevitably with nickel catalysis. Now, to do this, we need the photocatalyst to straddle the reactivity to reduce nickel 1 to nickel 0 on one end, and of course, oxidize the electrophile, functionalize both the electrophile and the nickel. And it needs to do both of these, right? So iridium DFCF3 straddles this lovely, very well, minus 1.37 on one end, plus 1.21 on the other end. Osmium does not. And of course, you can change the osmium catalyst to a more reducing one instead of a more oxidizing one like this. But because of the triplet energy, this bar is as big as it is, right? You can do the math between minus 1.37 plus 1.21. That's 2.58. Minus 0.6 plus 1.22 is 1.83, right? So we needed this bit to straddle this bigger, but what that means is we need a different photocatalyst. By the way, Rubipi I've illustrated here next to iridium DFCF3, but I would argue given its triplet energy, it really should be next to the osmium. And that tells us that there's an opening for more photoredox catalysts in right here. So I had a talented postdoc that took on this challenge several years ago, and there was a complex that was published in literature in organic chemistry in 2006, this heteroleptic iridium complex, which had a spin forbidden excitation in the green, 525 nanometers. And there was a computational paper that told us where the HOMO and the LUMO was on this structure. And that led Eva to manipulate these 3 groups independently of each other, the NCN ligand for the LUMO, the phenylpyridol for the HOMO, the halide for stability. And she identified 2 workhorse catalysts. This one is the more reductive one, 566 nanometers in the orange. This one is a more oxidizing one, 587 nanometers. These are now, by the way, commercially available from Enamine if anyone is interested in these. Uh, with this left iridium catalyst, by the way, this straddles reactivity where it'll reach to turn the nickel catalyst over, but it'll also activate the alkyl functional group. So Ava left and Kitty joined the project. She demonstrated these benzyl trifluoroborate cross couplings with aryl bromides driven by this iridium photocatalyst, responsive again to low energy light, 595 nanometers in the orange. The scope of this is perfectly reasonable. There are some functionality, including this fluorinone, which you can imagine will absorb blue light, but they do not absorb orange light, so orange light is more tolerated. We also demonstrated Kotrytsky salt cross-coupling. These triphenylpyridinium Kotrytsky salts will cross-couple with aryl bromides, again driven by nickel as a catalyst, the iridium photoredox catalyst. By the way, this was published by Molander originally with a different catalyst. Under his conditions, this chemistry works great. But if you use the blue light iridium catalyst with orange light, the chemistry does not work. And the scope of this is also perfectly reasonable, including tolerating some reactive functionality like an aryl nitro here, and as well as things that look like drug-like or drug-derived scaffolds. One vignette that we're still working on that shows, I think, some of the potential for this chemistry. So these diazarines are used ubiquitously in chemical biology because, of course, under thermal and photochemical excitation, they generate carbene, and that carbene cross-couples extensively. How you make the diazarine, by the way, you make a trifluoromethyl-acetophenone, you condense it with hydroxylamine, you add tosyl chloride, ammonia, and iodine. 4 steps: nucleophile, electrophile, nucleophile, and oxidant, which is fine, and it works. But of course, imagine that your pink ball here is a complex structure. This chemistry would not work in the presence of that complex reactivity. So we wondered whether we can install the pink ball after the diazarine is made by a cross-coupling event, like, for example, what I just showed you. And in fact, that chemistry works with Kotrytsky salts and orange light and these orange light iridium catalysts. The yield is not quite where it needs to be yet, but it's promising. But if you look at the F19 NMR, that's the desired product. This is an internal standard. There's a little bit of gunk, but the corresponding blue light catalyzed reaction is just an absolute forest because the diazarine is not stable to blue light. So we're still trying to pursue this. One last story about this. We want to generate these functionalized coupling partners, and of course, for use in pharma and by others. And if you look at, there's various ways to do this online. We did this very recently inside the lab. Commonly available functional groups, commercially available functional groups ranked. Alkyl iodide coupling partners are not very available. Ethers are widely available. Alcohols, of course, right next to ethers. And the ones I really want to point to is the primary amines and carboxylic acids. And if you look at recent assays of reactions conducted in medicinal chemistry, by far the most common reaction made by medicinal chemists is the amide bond formation. Big surprise that the components of the amide bond, i.e. amines and carboxylic acids, are so widely abundant because, of course, commercial vendors see the possibilities to make money here. So if you wanted to use primary amines as coupling partners, there's 2 ways to do that. One is you make these Kotrytsky salts. These are reductively initiated, or we introduced this several years ago, these redox active amines, which are oxidatively initiated. Alternately, you can imagine using carboxylic acids as well, and they also need to be derivatized. Of course, one of the derivatizations is just a base to deprotonate that generate these carboxylates, which are oxidatively initiated to lose CO2 and generate the radical, or these redox active esters and hydroxythalamide esters, which are reductively initiated. So you have the possibilities to do both oxidative and reductive initiation to generate alkyl radicals from carboxylic acids. So we wanted to do that with orange light, and the standard iridium workhorse photocatalyst does this quite well, but again uses purple light, 380 nanometers. Under these conditions, this works great, 73% yield. Our more oxidizing iridium photocatalyst with orange light, 556 nanometers for the excitation, 88% yield. And we looked at the scope of this transformation, and it's reasonably general for proline. Orange light, the numbers in orange are with the orange catalyst, the numbers in blue are with the blue catalyst. If you have sensitive functionality like an oxime, you can isomerize it with high energy light. That's clearly avoided with low energy light. And then we looked at other some acids are problematic in this chemistry. In this case, this piperazine, the orange is better than the blue, but often blue is also perfectly reasonable, until you get to a carboxylic acid such as this one, which under these conditions simply didn't work. And this caused us to wonder, why this didn't work. And one hypothesis, of course, is you can imagine these aliphatic carboxylic acids are harder to oxidize than something like proline because the radical that's generated is not as stable. And we wonder whether that was true and the iridium catalyst simply can't oxidize these. It turns out that's not true. Our origin-light iridium photocatalyst oxidizes this carboxylate just fine, which then does simple Giza chemistry. So this led us to hypothesize that the problem here was not the oxidation, but rather the carboxylic acid was interfering with nickel. And in fact, we did the control experiment. We took the carboxylic acid that we know cross couples in very good yield, and we doped in the acid that we know is problematic. And as you increase the amount of B in the reaction, the yield of A goes down to the point where its equimolar completely shuts down. And that means that the chemistry is obviously sensitive to the structure of the acid. So we devised a second protocol, which involves in situ coupling to make these redox active esters. And without purification, we simply do the orange light cross electrical coupling to generate a wide variety of structures and good chemical yield usually. The numbers in zero is from the acid. The number in the orange is, of course, from this redox active ester, including some functionality that's difficult for blue, disfluorine. Again, blue light gives you much lower yield, and orange light lets you rescue this. So if you're interested, these iridium catalysts are now available from enamine. Here's the QR code for those that are interested, as well as some osmium catalysts that they're making available, including things that can be clicked onto more complex structures. I'll stop there. I thank the people that did the work on the individual slides. NIH and BMS and Merck we're grateful to them for the support, as well as my collaborators, some of whom I did not talk about their work. Lastly, thank you very much for the opportunity to be here. I'd be happy to answer any questions if there are any.
All right, thanks, Tom. Are there any questions? If you have any, there's a question and answer box at the bottom, so feel free to type one in. Alan, I don't know if there's anything on YouTube. See anything? So, how complex a system have you been able to, like I saw the pyridinium catalyst, or the pyridinium cross coupling. Have you been able to apply it to fairly complex systems, peptides, things like that?
We have several examples of peptides, well, simple peptides, dipeptides. We've done several typical, well, actually, we did the Merck Informer library on a different reaction. And we had more success with the Merck Informer library than other photoredox catalyzed reactions published by others. And I'll say no more.
Well, definitely, yeah, it seems like the scope could be considerably broader.
And I think, and as you know, Steve, the Merck Informer library has some really gnarly structures. And I think they're problematic for many of us, but we do better than most, but not perfect.
That's really nice. Oh, okay. So we have one question from Shengying Xia. Thanks for your talk. Do you have an idea why the acid in your last case didn't work? Are alpha nitrogen required for the decarboxylation?
It is not required for the decarboxylation. Let me just go back to that. I think why it didn't work, we believe, is that the structure of the acid influences how well it interacts with a nickel intermediate. So these proline carboxylic acids, probably because of sterics, although it's not so clear, are not very good ligands for the nickel. But these more naked acids, like the well, this is a piperidine carboxylic acid, are better ligands for the nickel. And I think at low stoichiometry, it's not such a big problem, right? This is entry. I don't know if you can see my cursor because the spotlight was not responding very well. At 10%, it impacts the yield a little bit, but as you get more and more of it, you start to shut down the productive reaction. This is a poison. This is a catalyst inhibitor. And the way to avoid it, of course, is you no longer have the carboxylic acid, and then we have the redox active ester, which still can be activated by the same catalyst.
All right. Well, thanks a lot. I think if there are any additional questions, you can type them into the Q&A, and Tom, you can answer them offline. And we can move on to Ohyun's.
Great. Thank you.
Thank you.
I was thinking, can you hear me? Good.
We hear
What
you.
great talk. That was wonderful. I really enjoyed it. You know, I was thinking in the list of the radical precursors, I noticed that the alkene was missing.
Sorry,
Um, in the list of precursors for making radicals under these photoredox cross-coupling conditions, I noticed that alkene was missing.
alkene.
Yeah.
Right.
Because we've done it internally of using these ozone-generated peroxides as a basically electrophile for cross-coupling, such as Suzuki coupling and other reactions, amination. They work perfectly fine. But in reality, the yields are actually better using just what we've been doing, coppers and irons without really any help of the external light sources. So we haven't really published it ourselves. I was hoping that someone will actually pick up this peroxide, as an electrophile because they really provide orthogonal functionality in terms of what they can bring for the alkyl portion, especially chiral and initial pure alkyl groups for the cross-coupling reactions. So, yeah.
Absolutely.
Okay, I guess Ohyun, can you share your slides, please? And we'll
Course.
get started.
Okay, let's get the screen share.
So before you get started and while you're getting set up, I'll do a little
Uh,
brief introduction on you.
Sure.
So our second speaker of the day is Professor Ohyun Kwon, who is currently a professor at UCLA. Ohyun earned both her BS and MS at Seoul National University in South Korea, after which she came to the United States to pursue her PhD at Columbia University under the guidance of Professor Danishevsky. There, Ohyun worked towards the synthesis of biologically relevant glycolipids and complex terpenoids. As a Howard Hughes postdoctoral fellow, Ohyun studied chemical genetics in Professor Schreiber's lab at Harvard University, accomplishing the diversity-oriented combinatorial synthesis of a library of multicyclic compounds and macrocycles. In 2001, Ohyun joined the faculty at UCLA, where a group has focused on the design and development of novel reactions and reagents that enable the synthesis of natural products and unnatural small molecules of medicinal significance. Ohyun's group is well known for their work in the realm of redox-based deconstructive radical chemistry, as well as their work related to phosphorus organocatalysts and ligands. And today, I'm very excited that we'll hear about synthesis through CC scission. So take it away, Ohyun.
All right, thank you so much for that introduction, Alex. It's my great honor and pleasure to contribute to this virtual symposium series. So as Alex has mentioned that we have two distinct programs in terms of chemical methodology development, although we also do a lot of total synthesis as well as chemical biological studies as well. So organic synthesis, which is what we are most interested in our lab, is a very old discipline. Some will say that it's about 200 years old. And even when I was in grad school, we declared that we can make pretty much any molecule given enough resources and time. However, we all know that organic synthesis is not trivial, even for a very simple molecule. So if anybody asks me what is the remaining challenge in organic synthesis, I would argue that it may be making molecules in initial pure form. So let's look at one example. This particular amine that I have here at the top right is a chiral amine, but to a well-trained synthetic organic chemist's eyes, you can tell that this is not an easy molecule to make initial pure. Why? Because in general, making point chiral molecules, you'll have to distinguish from the right and left, and the difference between the right and left in this amine is minuscule. It's CH versus CH2. So if we examine the ways of making this molecule from 30 years ago, people had used basically a chiral pull approach, where when you look at this amine, you ask what is out there that looks resembles the amine structure, and how do we convert the chiral molecule into the amine in a specific fashion. So Kane and Coach and Han in 1992 got plus limonene. And if you look at the structure between the limonene and that chiral amine, is that the isopropenyl versus amino group, and the remainder of the molecule is identical with the inversion of that chiral center. And since there was no chemistry to cleave that particular carbon-carbon bond and replace that with carbon-nitrogen bond, now they are doing stitching together known chemical reactions to convert isopropenyl group to amino group. First of all, there are two double bonds in plus limonene, so you have to protect one of the double bonds that you don't want to convert, which will be trisubstituted and more electron-rich double bonds. So controlled equivalence of MCPBA will execute selective epoxidation of that double bond and then have the isopropenyl group remaining in 63%. Ozonolysis will convert isopropenyl to acetyl, set for the subsequent Baeyer-Billiger oxidation using MCPBA again, which occurs with retention of cell chemistry from acetyl to acetate. Now, the epoxide is now deprotected using zinc acetic acid back to alkene. Now, acetate is not a particularly good SN2 leaving group. Therefore, it is deprotected using LAH, followed by tosylation, providing secondary tosylate. And sodium azide will do the SN2 displacement of a tosylate with complete inversion of cell chemistry, and that resulting azide is reduced by LAH to the desired amine. Phew, so that's an 8-step conversion. I would argue that it's a pretty good synthesis. Every single step is straightforward, perhaps spot-to-spot conversion, and chemicals that we all have in our labs. Now we come to 2020s, and chemistry that we just talked about is not really sexy. So what you want to do is asymmetric catalysis. You can take your bio, organo, transition metal catalysis, and Qing Lu at Tsinghua University in China decided that he is going to do cobalt catalyzed isomerization of the double bond into an alternative double bond. This is a beautiful chemistry, efficient with 93% yield and 83% EE. And perhaps you can enrich the EE by perhaps recrystallizing the phthalimide product. Of course, phthalimide is easy to deprotect to the corresponding amine. Now, the particular C2 symmetric alkene is not a commercially available compound, nor it is a natural product. Therefore, you'll have to make it. You make it from the corresponding alcohol via PCC oxidation and video raffination, and that particular hydroxyphthalimide is also not commercially available. Therefore, it comes from non-natural product, commercially available amino alcohol, and then go through the 5-step conversion, including this beautiful cobalt catalysis. So if you just look at the manuscript or paper, it might look like this is an improvement with a cool catalysis reaction using abundant base metal catalysis. However, chirality has to come from somewhere. So the cobalt is a chiral complex, meaning that it has a chiral ligand on it. So if you examine the supporting information of the article, you will find that the chirality ultimately comes from alanine, and alanine is reduced to alaninol, which itself is commercially available compound. And then alcohol is converted to the corresponding chloride using dionyl chloride. Amine is protected for the SN2 displacement of chloride using anion of diethyl phosphine. And then the protecting group is released to deconvolute the free amine, which is condensed with aldehyde, and then diol reduction of the imine gives the chiral tridentate ligand, which is complex with cobalt dichloride to get the chiral cobalt. Now that itself is an 8-step synthesis. So imagine that you are a company and you need to provide this agrochemical for experiment, maybe have to spray them in the field. And if you have to provide the 10 kilo of this particular amine, just think about which synthesis you will do. And if your answer is the top one, have we really made a progress? However, what would you say if I tell you that actually we could do what I just earlier described, that is a selective conversion of this particular carbon-carbon bond, removing isopropenyl from limonene oxide. And through the reaction that we named amino dealkylation, we can replace isopropenyl group with phthalimide in an efficient manner. And this particular diacer isomer is isolated in 56% yield. And then deoxygenation using rhenium oxide and phosphite. And then hydrogen deprotection of the phthalimide provides that amine that we've been talking about, which is about $2,000 per gram. But if you think about how it was made previously, perhaps $2,000 per gram is a bargain. So today, what I want to talk about is that how my group came about with the idea of cleaving a particular carbon-carbon bond in the soup of, in the presence of a multiple carbon-carbon bonds of the molecular framework, and being able to convert it to amine. And as you will see, you can pretty much convert that carbon-carbon bond to any bond that you desire and you need. Now, this is a only 30-minute talk, and my actually presentation supposed to be a 15-minute talk. So I will not actually go into details of the following about 20 slides, but I just want to give you an idea as to how we come up with this particular type of approach. And I want to go back to our phosphorus organocatalysis program. As Alex mentioned earlier, that we have developed and published over 30 different nucleophilic phosphine catalyzed reactions. Most of those reactions will generate chiral, cyclic, heterocycles, and carbocycle molecules. And we wanted to generate those chiral molecules in initial pure form. Therefore, we created some chiral phosphines. Now, of course, there are many commercially available chirophosphines, which are usually expensive, but perhaps more importantly, at the time about 10 years ago when we were developing our chirophosphine, they are usually bidentate ligands for transition metal catalysis, which is unnecessary for nucleophilic phosphine catalysis. Monodentate phosphine is perfectly okay. Moreover, P-chirophosphines are quite rare and difficult to prepare. So we had an idea of preparing these P-chirophosphines that are very rigid in its structure and therefore well suited for organocatalytic reactions using chirophosphines. So the synthesis starts from L-hydroxyproline, natural amino acid, converted to tritosylated hydroxyprolinol, and then dialkylation using dianion of monophosphine will provide this 2-to-1 bridged bicyclic HIPFOS that we named because it comes from hydroxyproline. And it's a very efficient and short synthesis, and perhaps as importantly, a modular synthesis. At the very last alkylation step, depending on what type of monophosphine we use, we can have a different protecting group on the phosphorus. Of course, we can also have a different protecting group on the nitrogen. So Sigma Aldrich provides and sells these chirophosphines, and here are the list of available chirophosphines. As you can see, both exo and endo HIPFOS are available with different substituent on the aryl group, as well as an benzyl version of the p-phenyl HIPFOS chirophosphines. Now, we have used in our lab of these chirophosphines in total synthesis and as well as some drug development projects. Again, I'm not going to go into the details of these total synthesis. However, what I like to emphasize here is that HIPFOS that we generated and also Sigma Aldrich now produces and sells, these are derived from L-hydroxyproline. In other words, they only exist in one enantiotic form. Now, natural products can have a different chirality. And whenever we are applying HIPFOS in our asymmetric total synthesis of these natural products, we are nervous because chances are 50-50 that absolute configuration of the hydroxyproline might match with the necessary absolute configuration of the resulting product, or it could be the opposite enantiomer. Now, Ian completes plus ibophyridine synthesis using natural natural amino acid derived HIFAS that's commercially available from Sigma Aldrich, and can execute this imine and alinoid annulation in a highly efficient and enantiomer selective manner, allowing us to complete the total synthesis. In another example of minus actinophilic acid total synthesis by Ling Chao, we can again have matching absolute configuration of paramethoxyphenyl and the HIFAS to generate highly efficient and highly enantiomer selective dihydroperol synthesis for completing the total synthesis of minus actinophilic acid. As I mentioned to you at the beginning, my group does chemical biological studies, and one of the platforms that we really like to work on is doing phenotypic assay on zebrafish embryos. So zebrafish embryos are whole animal, these are vertebrates, and as the embryos, the eggs are really small, we can array them about 3 or 4 in each 96 well plate. And then as we screen these each well with different chemicals that we created from the phosphorus organocatalysis, we are inducing interesting biology, and we are paying attention to the disease-related biology. So in a particular assay using wild-type zebrafish embryos, we identify this particular molecule that we named as aplaxone, inhibiting vein precursor plexus formation in zebrafish embryos in the tail part. Without going into too much of biology, I can tell you that we discovered that aplaxone can inhibit cholesterol biosynthesis in zebrafish. Now, statins are very well-known drugs that inhibit HMG-CoA reductase, the best-known Lipitor by Pfizer. And we wanted to compare the potency of aplaxone to that of Lipitor for cholesterol biosynthesis inhibition. So if you look at B, here's the cholesterol level at 100%. And as we have 10 micro aplaxone and Lipitor, it seems that aplaxone is more potent. When you go to 40 micromolar, aplaxone was definitely more potent than Lipitor for cholesterol biosynthesis. Now, aplaxone is a chiral molecule, and to show that it's not any general enone-related promiscuous function, that we wanted to create aplaxone in enantiomer selective fashion. So previously, for the dihydroperol synthesis in two total synthesis, we needed endo configuration of HIFAS, but for the 4+2 annulation using alpha-methyl or alpha-alkylalinoate with the imine to make tetrahydropyridine, the exo configuration of the HIFAS was necessary. And this particular enantiomer is L-hydroxyproline derived, therefore it's a Sigma Aldrich commercially available. The mirror image, however, is not commercially available, and we made that from the D-hydroxyproline, which I will talk about a little bit more later. And using paramethoxyphenyl exo HIFAS, we can generate this particular tetrahydropyridine carboxylic ester with high EE, and TABI olefination and hydrolysis of enoreser provides R-aplaxone, and then the mirror image catalyst will provide S-aplaxone. And of course, like in the total synthesis, we are hoping that R-aplaxone will be the active component of this cholesterol lowering effect, and it was. So here's again cholesterol level for the control 100%, and racemic aplaxone was inhibiting 20% at this particular concentration. R-aplaxone about 40% inhibition, indicating it's twice as potent. And then S-aplaxone has no activity, and this is again Lipitor, less potent than R-aplaxone. So we are very happy. In another zebrafish assay, we are now screening zebrafish embryo that is a mutant named as Trembler. It's named Trembler, because its heart is fibrillating. So this is an anti-arrhythmia. This is an arrhythmia model in fish. So heart is twitching. When we treat this fish with a F7, this particular small molecule, we see the heart restored function with regular beating. we are really excited, and we actually did deeper chemical biological studies to finally isolate the target protein, which turns out to be VDAC2. Without going into much details, we basically figure out that F7 through potentiating VDAC2, this is a mitochondrial outer membrane channel protein, should be able to rescue any form of arrhythmia. So we go to a human disease model in mouse, a disease called CPVT. It's catecholaminergic polymorphic ventricular tachycardia. What it is that these patients will have ryanodine receptor mutation, which is very important for the cardiomyocyte calcium homeostasis. And these people and these mice, when they have high adrenergic condition, their heart cannot accommodate fast beating, therefore they go into tachycardia. So for example, CPVT mouse, if you inject adrenaline, it goes into tachycardia or sometimes sudden cardiac arrest. However, if we pre-treat mouse with F7 and inject adrenaline, the EKG stays completely normal. So we are really excited about this hit. We also did docking studies of the protein with the drug F7, identifying some key hydrogen bonding amino acids in this study. We also created the VDAC2 knockout mouse to show that every single wild-type mouse group were surviving for a long time. However, VDAC2 knockout mouse die one by one, the entire group by week 2, and every single one of them die of heart failure, indicating VDAC2 is a very important protein for heart function, which, by the way, was unknown in the world of biology, even if there were over 1,000 publications on VDAC2 at the time that we started our project. Now let's go back to chemistry. So F7, again, is a chiral dihydroperol molecule. And as you've seen in two total synthesis, to make enantiomer enriched dihydroperol, endo configuration of the HIFAS is efficacious. Therefore, when we have endophenyl HIFAS, we get 72% EE of dihydroperol. With exo, we get only 52% EE. Now, what's important, however, is that both endo and exo HIFAS derived from natural amino acid hydroxyproline provides S configuration, which is the opposite of the desired enantiomer for the basically anti-arrhythmic function of F7. Now, you've already seen that we made enantiomer of those HIFAS starting from dihydroxyproline in the Aplexone project. So you would say that, well, you can make the other mirror image and make the F7, and by modulating substituents on the phosphorus and nitrogen, we will easily be increase the enantiomer selectivity of this particular reaction. However, if you compare the price of the starting material, L-hydroxyproline being natural product and dihydroxyproline being unnatural product, you can see that it is about 765 times more expensive. And we didn't like the idea of that we are relying on this very expensive starting material to make our catalyst for the drug production. So we start to question if there are sources of chiral molecules from nature, abundant, inexpensive, and could exist in both enantiomer forms. And most people think that natural products only exist in one enantiomer form in nature, such as carbohydrates and amino acid. However, the most abundant class of natural product is terpene. Terpenoids consist of 60% of all natural products. And it just so happens that monoterpenoids usually exist in both enantiomer forms in multiple plant sources. A poster child of such a fact will be carbon. R-carbon is isolated from spearmint leaves, and S-carbon is isolated from caraway seeds, although they are existing in many different plants as well. And if you look at the price of R-carbon, it's $31 per kilo. So this is plant-based, renewable, environmentally friendly. You can throw in any fancy words, but the bottom line is that we now have both enantiomers as our starting material. In other words, we'll be able to make both chiral phosphines for any necessary chirality of our catalysis product. So here's the chemistry that was already known in the literature. And Muti converts R carbon via a known procedure to this cyclopentane diol for the dialkylation chemistry. So you get the diol, dimethylate, and then if you do dialkylation, then you'll be making this 2-to-1 bridged carbophos, which has P chirality, just like in HIPAS. Now, the problem is carbon, just like many other terpenoids, are isoprenoid. And isoprene, a lot of times will have this isopropyl substituent. And that's not what we want. In particular, this cis stereochemistry of isopropyl group to the hydroxymethyl now makes this isopropyl to exist in the endophase of carbophos, blocking any formation of endophenyl carbophos. But you remember, for the synthesis of F7, which is diadoporol, endo configuration of the 2-to-1 bridged bicyclic phosphine is more conducive. So we are stuck. What do? Even if we make the other enantiomer, we will only get 25% EE. And this is when Muti leaves, take up a job at TCI America, and then Andy takes up the project. And then he says, oh, I do not like that isopropyl group. I want to just get rid of it. So after methylation, he will bubble ozone in methanol out in the open air of this bismethylate in methanol. And then after stopping the bubbling ozone, he will dump in some ferrous salt, ferric sulfate, and then benzene diol as an hydrogen atom donor, and voila, isopropyl group is gone. Once it's gone, alkylation will provide both exophenyl and endophenyl carbophos, and using paramethoxyphenyl endocarbophos, we can now make a efficient and enantiomer selective formation of RF7, solving the problem of drug production. But now this, we named as hydrodealkylation, is the beginning of the program where we go after a particular carbon-carbon bond cleavage for the synthesis of the resulting whichever molecule that we desire, in this case, hydrodealkylated product. Now, here's a mechanism for the reaction. As I mentioned to you, it's a one-part, two-step process where the first step is ozonolysis in the presence of methanol, and then second step is low valent metal single electron transfer reduction followed by fragmentation and then radical capture chemistry. You are all familiar with ozonolysis chemistry, 3+2, followed by retro 3+2. What is critical is the regional selectivity during retro 3+2, that it forms carbonyl oxide, known as Krigge intermediate, in such a way that you will have more electron donating groups on the carbonyl oxide. In other words, when you look at the structure of alkene, your starting material, you can predict where you will be having carbonyl oxide. And that carbon is where the methanol will capture before the second 3+2 cycle addition to make alpha methoxy hydroperoxide. Once you get the hydroperoxide, iron, ferrous, will do single electron transfer and then cleave the weakest OO bond, generating ferric hydroxide. And then alkoxy radical undergoes facile beta scission to generate methyl acetate. Now, methyl comes from methanol, and these two carbons are originally from the isopropyl carbon and methyl. And then now you are left with alkyl radical, which is predictable from the structure of the starting material. And as you've seen, we decided we're going to trap it with a hydrogen atom using benzene diol. The question is why? The why is in the starting material. Nature provides these monoterpenoids and then sesquiterpenoids. Many of them contain isopropyl substituent. As I mentioned to you, limonene oxide, isopyligol, dihydrocarbon, dihydrocarbyl. This is the Favorsky product from the carbophos synthesis. This is a diol that you already seen earlier. Betulin is triterpenoid with diol, Betulinic acid is hydroxy acid, and all of these contain isopropenyl group, and sometimes you don't want it. And then we can cleanly chop off of that functionality in the presence of any given common organic functional group. This particular decalinone is nucatone, another natural product, which we can remove isopropenyl in the presence of enone. And these compounds are readily arrivable from 1 or 2 steps from the terpenoid, monoterpenoid starting materials. Now, I want to highlight one example to drive message home. This particular 3-methylcyclohexanol, surprisingly, is $1,500 per gram used in the androgen modulator synthesis. However, the starting isopuligol is 11 cents per gram. So this particular hydrodealkylation converts 11 cents to $1,500. Just like that, in a very efficient manner, 89% was isolated yield for a 20-gram scale reaction. Now, it doesn't have to be isopropenyl. It can be any double bond. And you apply the logic of both the ozonolysis, retro 3+2, and then the beta scission, where you will always have a more substituted electron-richer carbon for the hydroperoxide. And then CC to CH conversion. If you take campene, you will make this methyl carboxylic ester. If you take beta-pinene, you'll be making this cyclobutane methyl ester, methylene adamantane, caryophyllene oxide. You can also take alpha-pinene, nopor, vervinol, and sidrine, and all of these compounds are available in both enantiomer forms. And then you'll be producing this chiral aldehyde, in our case, protected as ethylene glycol, because the molecular weight of these compounds are too small. We basically just rotobap them off, and therefore we protect them for the ease of isolated yield report. Reaction is quick, and as I mentioned to you, we only use a slight excess of ferrous as well as benzene thiol for this particular reaction. If you are not convinced this reaction is useful, in the past, people will have to do multi-step conversion for the removal of isopropenyl, because a lot of times people are doing enantiomer-specific total synthesis using chiral starting material. And then monoterpenoids a lot of times will have isopropenyl. And in this particular case of bupropion total synthesis, people have to remove this isopropenyl of this keto ester, which took 6 individual steps. But of course, we will do it in one pot as hydrodealkylation. And we can find many such examples in the literature from 70s and 80s and 90s and even 2000s. And it seems to be people are picking this up. And now, when you have to remove isopropenyl group, people can utilize our hydrodealkylation. So these are the recent examples from literature where people are using hydrodealkylation either in total synthesis or natural product derivatization, or in this case, Alison Wendelet converted the peptide isoleucine motif into alanine by her chemistry of desaturation and then our hydrodealkylation. Now, because we are getting alkyl radical, now you can pretty much do anything with it. You can do cross-coupling, you can do radical capture. In this particular example, we are capturing with disulfide. I want to stress the fact that it actually requires 3 equivalent of disulfide, and then we can make the thioether. The only thing that I want to point out here is here's a dihydroleucine peptide derivative as our starting material, or sabinine, another natural product that I have not shown to you, as well as 2-carine. These are all monoterpenes. Now, this is my favorite reaction among all the dealkylation chemistry. We named as oxodealkylation. In its essence, it's converting CC bond of alkene onto CO double bond. How? It's a 3-step, 1-pot process. So as we generate with the ozonolysis and ferrous of the alkyl radical, we capture that with the TEMPOR radical. So then from this dihydrocarburyl, we'll be generating this aminoxylated product. If you just isolate that and do the reduction of the NO bond using zinc acetic acid, you will be generating that particular cyclohexane diol, which perhaps will be very difficult to make de novo. However, what Andy decided to do is just dumping acid. This is magnesium monophthalate. So if you oxidize your alkoxyamine to amine oxide, it will undergo cope elimination in the pot, going directly from isopropenyl to ketone. And using limonene oxide and beta elimination of the resulting ketone, we can generate this particular methyl hydroxycyclohexanone. And we can also make this particular cyclohexanone with 2 carbonyl, 1 protected. And these are all enantiomer compounds. And of course, starting materials are available in both enantiomer forms. And you can see that these compounds will be non-trivial to make enantiomer forms in both enantiomer forms readily. So hopefully this will be very useful compounds for a variety of applications. We can go from alkene to alkene. Again, in this case, the reaction yield was not very high. So we actually had to now switch the radical file, in this case, nitroolefin for addition elimination, and use alkene as an access reagent. If we do, we can now convert isopropenyl to a different kind of alkene for applications either in the drug synthesis as well as natural product synthesis. Now, although I have shown you the mechanism of the dealkylation chemistry, what I haven't talked to you about is the rate of each individual reaction. The radicals are very high energy species. And if it doesn't have a benzene thiol or tempo where the capturing is 10 to the 8 of very fast radical files, radicals can undergo side reactions such as further oxidation to alkene, disproportionation, and dimerization. These are all 10 to the 8 and 9 of per mole per second reaction rates. However, for the disulfide, as you've seen, we had to increase the equivalence of disulfide because it reacts at a rate of about 10 to the 5th or slower, as well as nitroolefin, and then sulfone, alkynyl sulfone. These are all slower than 10 to the 5th. Now, this is still super fast reaction rate compared to a lot of reactions that we do in our labs. However, relatively speaking, these are too slow, 1,000-fold slower than any side reaction radical can undergo. Therefore, our circularity ion condition was not conducive for efficient capture with these inefficient radical files. Therefore, we had to do catalytic ion with the circularity vitamin C. That way, we are generating radicals slowly. We are also minimizing ferric hydroxide concentration, which will oxidize radical to the corresponding alkene. And that's why we are now adopting catalytic ion with circulating vitamin C to use catalytic ion and quickly return it back to ion 2 to prevent side reactions and prevent the high concentration of alkyl radical and increase the relative concentration of radical files. Calcium chloride, which we can use as a chlorine radical source, is also about 10 to the 5th, which indicates that we'll have to do catalytic ion vitamin C for the dealkylative halogenation, halodealkylation. And we can do chlorobromoiodination quite efficiently. I just want to highlight one particular example. This particular bromide was used in a synthesis of vitamin E. And people will have to do this in 4 steps to convert this alkene to the corresponding bromide. But of course, we know which carbon-carbon bond and which radical will be generated based on the substitution pattern of this tri-substituted alkene. Therefore, we know we'll be making bromide via halodealkylation. Finally, I come back to the reaction that I've shown to you earlier at the beginning of the talk, that so far I've shown you ion-mediated single electron transfer reduction processes, but copper is also very reducing. In fact, the Q+ is more reducing than ferrous. So imagine that you have copper 1 in the presence of amine as your nucleophile, your peroxide as an electrophile. Single electron transfer will cleave OO bond, generate alkoxide, and then Q+ will become Q-puric, and then resulting alkyl radical conjoins as copper 3, and then reductive elimination will generate aminated alkane with the recycling of back to copper 1. So this is a fully catalytic cross-coupling process. And I've already shown you one application at the beginning of the talk, but here's another example of the amino alcohol, which is over $3,000 per gram. Again, this might look expensive, but imagine how you would make this particular molecule in this particular enantiomeric form, enantiopure. In fact, in the literature, people took, again, minus limonene, and in 12 steps, they could make that particular amino alcohol. Or you can start from isoprene with methyl acrylate, doing de novo and resolution in between to make enantiopure amino alcohol. But you will imagine what we will think. We will look at the literature, in the nature, and then say, which alkene can we convert to that particular amino alcohol? And we take dihydrocarbon, which is commercially available at $3, and then ozonolysis followed by copper chloride, phenanthroline, nothing else, just inositronitrile with phthalimide at room temperature. In short order, we can make this phthalimide dealkylated. We isolate this particular diacer isomer in 61% yield, and then deprotection of phthalimide provides that particular amine. Now imagine, alkene is the second most abundant functional group in all natural products. And any alkene in nature, as long as it follows the ozonolysis logic, we can convert it to the corresponding amine. So citronello will become this particular amino alcohol, which has never been made in enantiopure. The racemic, this deceptively simple cytosymmetric, pseudo-cytosymmetric amino alcohol is about $1,000 per gram. Now, this will be first enantio pure synthesis. Phytol, you've already seen it in hydrodealkylation. This particular carbon will become carbon-nitrogen bond and then beta-pinene. So any alkene can provide you with corresponding chiroamines. Now, it doesn't have to be natural product. We took the natural product because they are there and they are readily, cheaply available. You can take alkenes. Alkene is also very abundant in commodity chemicals, petrochemicals. For example, alpha-methylcytidine is a byproduct of a cumin process, which is an industrial process to make phenol from benzene. It's produced 300,000 tons annually worldwide. And we take that. If you apply the logic of ozonolysis, this carbon will become formaldehyde during the retro 3+2, and that carbon will become methoxyhydroperoxide. And as you do beta scission with Q+, then between phenyl radical and methyl radical, of course, methyl radical will be more stable. Therefore, with methyl benzoate byproduct, you generate methyl radical. So we use industrial byproduct as a source of methyl radical. Our reactions are very functional group tolerant, as you've seen in substrate scopes. So for example, we can take canonical nucleoside to N-methylation. So adenosine is 9.7 cents per gram, and all literature synthesis of N6-methyl adenosine bear protection of the alcohols to do selective N-methylation and deprotection, but we can do it without any protection of the alcohol under our amino dealkylation condition, converting 9.7 cents to over $100. And you can take deoxyadenosine, and also you can dimethylate. You can take cytidine or deoxycytidine or some anti-HIV drug. And if you have deuterated alpha-methylcytidine, you can generate CD3-related N6 CD3-related adenosine, which is over $7,000 per gram. Now, for the sake of time, I'm not going to go through the mechanism, which is really intriguing reaction, that it's actually not as simple as I just shown to you. A very interesting ion pair synergistic mechanism. And before I close the talk, I just want to tell you that it doesn't have to be alkene. Ketone is another very abundant functional group in synthetic intermediates, in commodity chemicals, and in natural products. 16% of all natural products have a ketone functionality. In other words, there are abundant chiral pool of ketones. And again, we can convert ketones into the corresponding radical via acylative radical functionalization. So imagine you take ketone and then condense it with hydrogen peroxide, converting it to the gem dihydroperoxide. And if you throw in low valence metals or photoredox or any reductant appropriate, you'll be cleaving OO bond, again generating alkoxy radical, undergoes beta scission, generating alkyl radical with a per acid, which gets further reduced to carboxylic acid with a radical file capturing that radical. Now here we are showing 14 natural product synthesis, 2 drug synthesis, and 1 natural product analog synthesis. And we show 9 different modalities of radical capture, including nickel catalyzed cross coupling for a drug synthesis. So for example, if you take pregnenolone and if you do hydrodeacylation, again, the most substituted carbon around the ketone will become the radical, and then substituted with hydrogen, that's androstenol, often oxidation of that alcohol, enol, will become conjugated androstenone. Sclariol can be converted with tetracetate and ozone onto the corresponding metal ketone with formate, and hydrodeacylation will provide cleaved of the acetyl of this compound, which was previously made in much longer sequence. And if we do treat with iron sulfate heptahydrate in the absence of radical file, then that radical will be captured by the alcohol, making etherification of ambroxide, which is a natural product and also very highly prized fragrance. Methylbetchlinate is a natural product. And then if you do the PCC oxidation of the alcohol, you generate the ketone. And then if you do deacylative dehydrogenation, then hydrogen peroxide and then iron sulfate heptahydrate and TEMPO, instead of capturing the tertiary alkyl radical, the steric congestion allows TEMPO to hydrogen abstract and then generate the corresponding isopropenyl, which is methylcelluloside, previously made in longer sequence as well. In this case, with cholestanol, we do TEMPO capture as aminoxyl, and then MCPB oxidation to the aldehyde, pinic oxidation, methyl ester synthesis, Dickmann condensation, and then alpha hydroxylation makes the first order synthesis of phosphasterone B. And heparin can be converted into the chrysanthemate using, again, dehydrodeacylation. In this case, we are doing the radical capture with the cupric and then beta hydride elimination to make that vinyl and then Groves metathesis. In this case, cleaving the CC bond, we capture that with allyl sulfone to make this allylated dihydroperol, and then reduction, and that is an intermediate that was made for the alkaloid synthesis in much longer sequences as well. And in this particular slide, we show that from sclariolide of that methyl ketone and hydrogen peroxide treatment, this crude product, which is quantitative clean conversion, not only we can do hydrodeacylation for the natural product synthesis, we can do the Giese addition of radical capture to the benzoquinone to make natural product and reduce it or eliminate acetate, but also we can capture that radical with disulfide to make the SHIP1 modulator drug, or we can capture that radical with boronic acid on the nickel catalysis to do antifungal reagent synthesis. So I come to the final slide where I have the members of my group as well as the light gray former members of the group whose work that I presented today. And I also like to thank all the funding agencies and collaborators of Dr. Chen, Schroeder-Secker, and Drekos on the zebrafish related studies. And finally, I'd like to thank Steve and Alex and Alan and your help for today's talk. And I don't know whether we have any time, but I'd be, of course, happy to answer any questions. Thank you.
Thank you so much for a fascinating talk. Do we have time for maybe one question from the audience? Okay, if anyone has a question, maybe please add it to the chat.
Shall I stop share if there's no questions?
Yes.
Okay, great.
Okay, I guess if maybe our panelists have any questions. If not, I guess we'll wrap it up here. So thank you so much. There is one question.
Oh, there is a
So
question.
yes, so thanks for your talk. Is it only limited to N-methylation? Could you do N-alkylation?
Of course. So the entire paper is about N-alkylation. So all the radicals that we've generated that I've shown in previous hydro, thio, oxo, halo, alkenyl, alkynyl, all these reactions, we've done the amination. But for the sake of time, I'm not showing the entire substrate scope, but rather leaving it to your imagination. So actually, the second table of that article that we published is actually the table of all the alkenes that I've shown to you in other reactions, such as isopuligol or nucatone. All these compounds are amenable for amination chemistry. So the answer is resounding yes.
Thank you so much for the question and answer.
Yeah, thank you for the question.
All right, so on that note, I think maybe we should bring it to a close now. But thank you so much to our speakers. We really appreciate you being here and sharing your science. Of course, thank you to everyone who attended, our audiences, Alan and Hugh for your support, and broadly the ACS and the CIC for their support. We'll see everyone in May.
Thank you.
Thank
Bye-bye.
you. Bye.
I'll see you guys later. I have to run to another meeting. Thanks a lot, Alan.
Okay.
Thanks a lot,
Okay.
Alex.
No problem.
All right, bye, everybody.
Bye. I'm about to end it now. I've stopped recording, so nobody can see it. So.